Hello everyone, welcome to Research Innovation webinar, and today's topic is focusing on the polymer characterization by analytical pyrolysis technology. This presentation is given by two speakers, and Dr. Karthikeyan Sutrignan and Professor Shogo Kumagai-san. I welcome you all, and as pleased to inform you that this webinar is sponsored by Frontier Lab, and analytical instrument supplier based in Japan, and which has 30 years experience in this analytical equipment. Let me quickly introduce to you about Technobiz. Technobiz is a company based in Thailand, which is organizing this webinar. It is International Resource Center for Polymer Industries and Process Technologies. We offer training, conference, exhibitions, publications, and webinars and consulting. Our focus is on the business focus on the polymer industry, rubber, plastics, polyurethane, and also the process technologies focusing on filtration, separation, water and membrane, and also energy and environment technologies. You can check more details about us at technobiz.org. Our webinars, we have three different types of webinars. One is a know-how webinar, which is focusing on the purely education. Another one we have today's webinar is focusing on the research innovation webinar, which is basically introducing research developments and innovations. And the other one we have is a technology showcase or tech showcase, basically to promote the commercial technologies to the target industry. You can check these websites for more information on our activities. Okay, today's webinar agenda is like this. We will have two presentations. We have two presentations, one by Dr. Karthikeyan, another one by Dr. Shogo-san, and then we have a Q&A session. The Q&A session, basically the way you need to ask questions, you need to type your questions in the question box, and both our speakers will address these questions at the end of the both presentations. So feel free to post your questions in the question box, and we will take these questions and let them answer appropriately. Okay, let me quickly introduce to you and show you the video presentation on the Frontier Lab, who is sponsoring this webinar. Please stand by.
Often, you are presented with a complex or unknown sample for chemical composition, failure, or contamination analysis. The organic analysis is fascinating but difficult to navigate. When you want to leave your home country and travel to the land of answers as your final destination, you will need a method map and guidebook to get you there successfully. Frontier Lab provides you with that method map and step-by-step guidance as you and your sample journey to the final destination. The method map applies to various applications. Virtually any material, solid, liquid, or gas, can be chemically characterized. No matter where your home country is, the method map will direct you to the land of answers effectively and efficiently. So it does not matter if you're coming from plastics and phthalates, paints and coatings, or oil and gas. Frontier Method Map will guide you to the land of answers. The method map is created using Frontier's multi-mode microfurnace pyrolyzer, EGA Pi 3030D. Unlike the majority of other analytical devices, the multi-mode pyrolyzer allows you to perform multiple analysis on one single sample, such as full-range evolved gas analysis, multi-step thermal desorption, true flash pyrolysis, double shot, hard cutting, and reactive pyrolysis. The microfurnace can be used for both isothermal and temperature program analysis. The multi-mode pyrolyzer also expands the application of gas chromatography instrumentations. It enables the analysis of the entire range of organic materials, including insoluble solids, as is without solvent, solvent extractions, or pretreatments. Using this technology, a sufficient amount of heat reproducibly breaks down the organic bonds of a complex mixture into smaller and stable molecules called pyrolysates. The pyrolysates formed and their relative intensities provide insight into the nature of the original material. The first step in creating the method map is evolved gas analysis, or EGA. A full-range EGA is performed using the microfurnace technology. to obtain the thermal profile of a sample for light compounds, volatiles, and additives, as well as oligomers, heavy, polar, and polymeric compounds. The EGA experiments can be done from 40 degrees Celsius to over 1000 degrees Celsius and correlate results to well-established thermal gravimetric analysis techniques throughout the entire temperature range of the experiment. This capability is critical for the evaluation of unknown samples. To perform EGA, a short and deactivated tube connects the GC injection port to the gas chromatography detector. The sample is dropped into the multi-mode pyrolyzer's furnace, which is set at a relatively low temperature. The furnace is then controllably ramped to a much higher temperature. Compounds evolve continuously from the sample as the temperature increases and directly transferred to the detector. A plot of detector response versus furnace temperature is then obtained. You have just completed your first step on your journey to the land of answers. So, EGA guides you on what to do next. It will show if thermal desorption, hard cutting, or flash pyrolysis is needed, or if a combination of the techniques is required. The next video shows flash pyrolysis and what sets Frontier microfurnace technology apart from other pyrolysis devices. Click here to keep watching and directing your journey to the land of answers.
Okay, that's introduction about the Frontier Lab. Okay, you can always check the more details at the website. Okay. Now, the first presentation, the first speaker, Dr. Karthikeyan Shatrugnan, is a consultant for the Frontier Laboratories based in Japan. Let me quickly introduce about him. He has a PhD in chemistry, having more than 15 years experience from both academia and industry with the leadership skills in technical and people management with reference to the laboratory and R&D environment. He developed a set of skills for the business development, channel management, marketing, and customer focus, and also laboratory operation, quality assurance, and also he's specialized in the environmental and food safety and experience in the implementing various quality management systems. He'll be giving a presentation on today's topic. Another topic is recent developments in analytical pyrolysis technology for polymer characterization. Let's welcome Dr. Karthikeyan Shatrugnan. Okay. Let me share his screen. Okay, Dr. Karthikeyan, it's all yours now.
Okay, Mr. Pram, thank you for the nice introduction. And good afternoon and good morning to every one of you. And welcome to a Frontier Lab webinar that is organized by Technobiz. And I'm sure that you will have some useful information out of this webinar that can be applied or practiced in your day-to-day work. My topic is actually, I'm going to discuss some of the recent developments in this analytical pyrolysis technology and how it's going to help some of the analytical challenges that we may be facing day-to-day kind of work. Before getting into the technical part, I just want to do a quick introduction to Frontier Lab, even though he has done it, so I will not take much time here. So Frontier Laboratories is actually a Japanese organization located in Kuriyama, Fukushima Prefecture, and it was started in 1991 by our president, Dr. Chu Watanabe. So these are the group of people who are behind the success of our organization. At the center, we can see Dr. Chu Watanabe, who is still feel young and want to do more to bring Frontier Lab to the next further heights. And we have offices in Japan and other parts of the world to cater our customers all over the world. We are global leading company in analytical pyrolysis, and we are the manufacturer of pyrolyzer and peripheral devices, including the ultralight metal capillary columns. Our area of expertise is obviously the polymer characterization with the multi-shot pyrolyzer using our unique ultralight column, And also we have another product line called actually Reactive, which comes in single and tandem micro reactors that can be used for rapid catalyst evaluation as well as the biomass research. But today our focus is on the multi-shot pyrolyzer. And Frontier Lab believe on partnership and collaboration, and we have many academic collaboration within Japan and outside Japan. These are some of our key opinion leaders who are behind the success of Frontier Laboratory in terms of the technology innovation. Now let me get into the technical part. So before talking about the research developments, for the benefits of some of the audience who may be totally new to the field or the concept of pyrolysis, I just want to spend some time to introduce pyrolysis as a concept and also as an analytical pyrolysis technology. Okay, what is pyrolysis? Pyrolysis is actually a Greek word. Okay, that means pyro means fire and lysis means a kind of separate. So what you are basically doing is you are doing a thermal cracking by breaking down the larger molecule into smaller molecules. Most of you may be familiar with the combustion, where the heat energy is applied in presence of oxygen or air, where it goes for the complete mineralization like CO carbon dioxide, which sometime may end up having a problem with the global warming if it is not properly managed. On the other hand, in pyrolysis, you are heating the organic matter in the absence of air or oxygen that allows you to break down the larger molecule into smaller stable molecule that may help or benefit to produce some valuable products in the range of like char or bio oil or syngas. So within the pyrolysis domain, there are two fields where a lot of work or developments happening. One is applied pyrolysis, the other one is the analytical pyrolysis. In applied pyrolysis, the pyrolysis is used as a process to produce some valuable products from feedstock or biomass, like what you see in this slide. So the pyrolysis process actually can be used to produce some valuable chemical from biomass or feedstock that can be further enhanced with some catalytic process. So even we have a system that can be used for such application, which probably we may talk in some other time. But today we'll be speaking more on analytical pyrolysis. So what is analytical pyrolysis? When you are using pyrolysis process as a kind of tool to characterize a material, then it comes under this analytical pyrolysis. How it is happening? So when you are using a micro furnace to heat your polymer or any biomass, where it is already like purged with the helium, so the outlet can be connected to any of the instrument technique that you are interested in. Here we have actually shown FTIR or mass spectrometry or GCMS. So that means you are able to, let me put the laser pointers. So when you are making any changes here by the thermal treatment, the evolved gases can be transferred to different instrumentation, and based on that information you are able to analyze the changes that is happening to the material that help you to characterize the material. This is all about the analytical pyrolysis. Let me explain with another kind of schematic. So if you are working in a laboratory with GCMS, it's easy to understand this part also. This schematic, actually the micro furnace is placed on top of the GC in the friendlet or the injection inlet. So the sample, when it is introduced to the micro furnace, which is set as a desired temperature, the compounds that are being evolved from the material will be swept to the GC column where the separation is taking place. Then with the help of suitable detector like MS or FID, you can get the fingerprint of this material. So if you are a GC user, the easy way to understand this pyrolysis GCMS is pyrolyzer can be seen as a sample introduction system for GCMS application, where you can introduce or analyze the solid sample or liquid sample without any pre-treatment or any other sample preparation. Okay, this is one way to understand the concept of analytical pyrolysis, where the pyrolyzer can be seen as a sample introduction tool. Let me explain this further. Okay, as I said, you don't need any sample preparation. That means you can transfer a representative sample, okay, by using appropriate sampling tool that can be transferred to a sample cup. Then this sample cup will be transferred or dropped into the micro furnace where the temperature is set for certain type of analysis. So what happens within the furnace, you have a kind of sample waiting position which is less than 40 degrees. That means the sample will be exposed to the higher temperature only when the analysis is starts. So what happens when you start the analysis, then this cup drops into the furnace, the hot zone or the heating zone, where it is being exposed to the high temperature, because of which the additives and also the monomers of polymers will be released from the material. Then they are being transferred to the GC column, where the separation is taking place based on the partial coefficient, and finally that is sent to the detector one by one. Then you get to see a kind of chromatogram. Here we call it pyrogram, that allows you to look at the different chemicals present in the polymeric material. So here basically we show this illustration for analysis of phthalates, okay, in plastic material, which is required as part of the RoHS. Okay, so with this illustration, I think even the general audience should be able to understand the concept of analytical pyrolysis, where we are using pyrolysis as a kind of process to characterize a material, okay, in combination with a suitable analytical technique like GCMS or FTIR and so on and so forth. So before talking about the recent developments, I just want to give some kind of feeling what are the common methods or techniques applied in day-to-day work. Mostly people are using the PY GCMS for analyzing polymer in different types of material. Okay, here is an example analysis of resin sample from a painting industry, where the customer is interested to know what type of polymer present in my resin sample. So in such case, you can do the flash pyrolysis directly. Okay, that will allow you to see the presence of different monomers, based on which you can tell what type of polymer present. In this particular sample, it has three types of polymer present. Okay, one is the polymethyl methacrylate, the polyhydroxyethyl methacrylate, and polystyrene. So even we can go for semi-quantitative analysis if we have the standard. So qualitative and quantitative analysis are possible with PYGCMS. Another common method is actually thermal desorption. Okay, most of the people are interested looking at the polymer as well as the additive in any of polymeric material. Here is an example of actually black rubber, which is used in tire industry. As you know, the additives are critical in tires performance because it has to have different combination of this vulcanizing agent or anti-degradant or antioxidant and plasticizer. So the customer or even the user, the tire producer, need to know the type nature of this material and the additives presence. So this can be accomplished by doing this thermal desorption with our PYGCMS. Okay, that means you are basically hitting the sample as a desired ramp rate from starting temperature like 50 or 100 to 320 degrees. Then later on you start the GC run for separation of these compounds. So in standard way of analysis, people are mostly using the PYGCMS for analysis of additives and polymers. Okay, now we are going to talk about the recent developments that is helping to expand the capability of pyrolysis GCMS application. In this slide, you can see a GC coupled with a pyrolyzer has got multiple accessories. Okay, so this is a auto sampler that can actually have or load 48 samples. So that means you are able to run 48 samples without your presence. That helps to increase your productivity. Okay, then we have different type of samplers, okay, that can be used depending upon the need that you require. Today we will be talking about two of these sampler. One is the micro reaction sampler, which I will be sharing some details later. Then we also have this UV radiator, which our fellow speaker Dr. Soge Kumege will be talking about. And we have this carrier gas selector that allows you to do the pyrolysis under air. Then you can do the analysis under helium. So those kind of things are possible with this carrier gas selector. And we have this selective sampler that allows you to do a hard cut, okay, hard cutting wall gas analysis GCMS, so which I'll be speaking today later. And this microjet cryo trap allows you to look at some of the very volatile compounds, because you are basically introducing liquid nitrogen to ensure that you are able to trap all these volatile in the column before the GC run starts. And we have a kind of a search engine or the software that helps you to interpret the data efficiently for 1000 over polymers and 500 over additives. Okay, and capillary column is something that we have that is made of the ultra alloy metal capillary column, which we cannot discuss much today, but definitely we will take an opportunity in some other occasion. Okay, today for our discussion, I stick to 3 different applications. Okay, the first one is the evolved gas analysis, and second one is hard cutting evolved gas analysis, GCMS, and the third one is the micro reaction pyrolysis, or or micro reaction sampler. Okay, so let's start with the evolved gas analysis. The evolved gas analysis, because it is self-explanatory by the term itself. Basically, you are trying to analyze the gases that are evolved from a material when you are thermally treating that material. Most of you must be familiar with thermogravimetric analysis, where exactly is happening this way. You are heating the sample, okay, from a start temperature to the end temperature at a given ramp rate, and you are collecting the information of weight loss information. Okay, then using this data, you can generate this temperature profile of the material by using this differential thermogravimetry. So what you get is actually the maximum peak height for additive group and polymer group. So this is basically tells you the temperature profile of the material. So you can get similar information and extra information if you are using evolved gas analysis. Okay, so in thermogravimetric, what happens? You are only collecting the information of the remaining sample. When you heat the sample, you do not know what is going out. You are only measuring with the electronic microbalance what is remaining. In the evolved gas analysis, it is just opposite. You are heating, and whatever is evolving, okay, that is being analyzed by your mass spectrometer. So you do not know what is left there. Most of the time you are seeing only what is coming out. That's why it's called evolved gas analysis. That also because you get a larger peak when more things are evolved, and you get a smaller peak when you have like less of additive. And the temperature also will tell you the temperature profile of the material. In addition, the peak over TGA versus here means different, because here you cannot get additional information from this peak except the temperature, whereas here this peak refers to the mass spectrum that can give you a lot of information that will help you to look at the degradation pathway or degradation kind of mechanism of any type of material that you are analyzing. Okay, this slide will give some better understanding on it. So when you do a evolved gas analysis, the output, what we call it, is EGA thermogram. When you see this kind of thermogram where you are getting the information, okay, how many peaks are there in my material, okay, and some of below 300 are generally classified as additives. Then you see anything above 300 can be a type of polymer. So the first information you are getting from your EGA or TGA is how many peaks and what temperature. Now the third and most important information what you can get from evolved gas analysis is the mass data. Okay, so you have this average mass spectrum that can tell you a lot of information about this material, and particularly we have a software, this FSearch, that has a database for evolved gas analysis for 1000 over polymers. So that means when you are trying to like navigate the nature of your sample and chemistry, you get 10-20% of the answer with the evolved gas analysis itself. So that will make your life easier to take the next step of analysis. Okay, this is how we see the evolved gas analysis will be very useful step when you are doing a pyrolysis GCMS analysis. I am going to give a couple of examples to have a kind of understanding how it is helping. So this is actually characterization of Chinese crude or crude propolis using evolved gas analysis. As you know, this propolis is a kind of resin-like material produced by this bee, and that has a lot of medicinal value. Okay, So when you do a TGA or EGA, you get a thermogram like this that tells, okay, you have a different peaks with different temperature. But for further details, one has to go to next type of analysis. But in the case of EGA, from this data, you can extrapolate for some information. Okay, in propolis, we are interested to know what kind of flavonoids present in this, because that is how they will see the value addition to this propolis. So here we have done this extracted ion thermogram for this particular mass charge ions that is referring to different flavonoids. Okay, so what we can see here, so this particular crude propolis has got most of these flavonoids that customer may be interested to see. So this is the kind of advantage or the value addition you can see. The EGA data will give more information on the chemical fingerprint of the method, the material, in addition to the temperature profile of the material. Okay, this is some key takeaway point that you have to understand. This is another example. Okay, we got a couple of plastic bags, okay, which they are claiming a biomass plastic bag. So before going to the detailed analysis, so when we do a EGA, so it can easily tell us, okay, one is the temperature profile, then it can tell, okay, only one of the bag has got this biomass-based material, the polysaccharides, whereas the other one, we do not see any kind of significant presence of this. So this is what, again, I'm emphasizing. The EGA MS help you to get some of the chemical information in addition to the temperature profile of the material that will help you to really take your next step during this analysis. Okay, now let me move on to the second application that I want to discuss today. Okay, we have started with EGA, and EGA, the question may come under what circumstance one has to consider EGA, because as I said before, if you are talking about a standard analysis of polymer for the presence of polymer or additives, generally you can go to flash pyrolysis or thermal desorption directly. But if you want to be more precise, then you need to know what is the temperature you want to set it for pyrolysis, or what is the temperature you want to set it for thermal desorption. Then it is better to start with EGA. Otherwise, we have a rule of thumb. Any polymer you want to do, 550 or 600 can be used for flash pyrolysis. Similarly, for thermal desorption, it can be 100 to 300. So this is general recommendation, but this may have to be varied a bit depending upon the type of sample and the analysis objective. Okay, this is where you have to decide under what circumstance you want to do a EGA. Once you have the EGA, then you know what is the next step, because you know your objective and you have the information to take your next step. So now let us talk about the hard cutting. That is another application where some of the accessories is helping to expand the capabilities of pyrolysis, the GCMS. Okay, for hard cutting, if you are a GC user, you would have heard about this two-dimensional GC, where you are trying to cut the first peak from the first GC column and transfer this portion to the second column for further separation. That means you are trying to get detailed information from one single peak by two separate kind of separation process. This is exactly happening here also. But in first step, we are not using a GC column, we are using a thermal, this micro furnace. So looking at the EGA data, you can decide what zone is more critical for your type of objective or where you want to get more information. In this slide, basically what we are showing, if you have a EGA of this nature with 5 different zones, and you can have generate 5 different chromatogram. Okay, by doing that, you are getting very clean chromatogram, that is one. So you can get all minute information that may be missed out if you are doing a flash pyrolysis for this kind of sample. This is actually sample coming from a cosmetics, okay, eyeliner, where the eyeliner performance will be like decided upon the moisturizing agent, what they use, preservative, and also the skincare kind of chemical and the polymer base. Okay, so here they always prefer to do this kind of hard cut to look at some of the minute information, which may not be possible to do with a kind of flash pyrolysis. So this is a situation where people are looking for hard cutting. Now, hard cutting, at least in terms of the concept, you are basically cutting the first peak from the microfurnace part, temperature zone, then you transfer this to the GC column for separation. Similarly, you repeat this for each zone, whereby you are able to get 5 different chromatograms from single sample. How is it working? So we have this accessory called Selective Sampler, because you have to have some kind of control which portion or which fraction you want to transfer to the GC and which portion you want to hold it. Okay, this is what the Selective Sampler can do it for you. The Selective Sampler has got a valve and also additional carrier gas. Okay, this carrier gas, when the sampling is on, this valve is closed, so that means your sample can be reaching the GC column directly. When the sampling is off, you get the helium gas flow from this selective sampler, and it will have a flow kind of split, and that will push upward also to ensure that you are not getting anything from the sample to the column, so no interference. So this is how this valve and additional gas line is helping to fragment or fraction the zone that you are interested to analyze by hard cut. I'm going to show one case study where this hard cutting EGA GCMS is helping to address the problem. Okay, we received a sample from polyvinyl alcohol manufacturing, where they suddenly found their batches are failed because of the higher turbidity. So they want to know what is the cause for this turbidity. Okay, they would have tried with other techniques, but we felt we can do an easy job for them. So as you know, generally, if you want to find some quick and dirty answer, we always try to do a flash pyrolysis. But what we can see here, the flash pyrolysis data is not giving the information what you are interested in, because by looking at this data, we feel that, okay, there is no difference between these two, but there is a difference in terms of the physical appearance and quality. So that means we have to go for a systematic approach that starts with the EGA. Okay, here we have started with the EGA, the evolved gas analysis for the standard and the turbid product. Okay, the failed product and the QC pass product. We can see there is a small difference in the EGA thermogram in the second peak. So this is a bit larger. And similarly, when we look at the average mass spectrum, that also shows that difference, because there are some ions that you are seeing here which are not seen there. Okay, but the information is not sufficient to tell the clear reason for this turbidity. That means what we can say at this point, there is a difference which needs to be analyzed further. So instead of doing a multi-zone or hard cut, what we thought it would be good, because we find difference only in this zone. So let us do the hard cut for this particular zone, for which you need to use a configuration like this. So you have a GC, then column, then you have micro furnace, and also the selective sampler and cryo trap, particularly to ensure that you are not losing any information. Okay, these are the analytical conditions which I am not going to read. So what we are doing is we are collecting the fraction, okay, that is evolved from 460 degree to 540 degree. Okay, then this fraction is being analyzed by the GC, and this is the total ion chromatogram, and this is the extracted ion chromatogram, where we see there is one kind of extra peaks that is seen in the turbid or the failed PVA, polyvinyl alcohol. Then we have zoomed further by using the SIM mode. Okay, in this SIM mode, we could see that this extra peak coming due to mass charge ratio of 57 is seen only in turbid polyvinyl alcohol, but not in. So we can say in a way, okay, this is the one that could be a reason for this turbidity. This is actually attributed to saturated hydrocarbon that may be coming from one type of polymer. Okay, but now the question, we do not know what kind of polymer. Then we went back to the customer and we told them, okay, this is what we are seeing, but we cannot say where is this coming from. Then the customer said, yes, this is the toll manufacturing facility where this was used for manufacturing of this ethylene vinyl acetate copolymer before this batch. That means because of insufficient washing, there could be some residue which is causing this turbidity. Then we confirmed this polyvinyl alcohol by spiking ethyl vinyl acetate, okay, real sample. Then we could see again this extra the saturated hydrocarbon peaks. So that confirms this is coming from ethyl vinyl acetate only. Then we also try to do a kind of semi-quantification for this turbid sample, where we found it's having close to 1000 ppm of ethyl vinyl acetate. That means now the customer can do a kind of protocol where they have to rinse the facility to ensure that their EVA concentration is less than 1000 ppm to avoid any kind of turbidity in future PVA manufacturing. So this is how it is helping the hard cutting GCMS. Now I just want to show another example, but I will not have the details here. Okay, this is part of the deformulation where a competitor is looking at the competitor product, okay, for the automobile coating material. And when we look at the EGA data, again at zone 2, there is this difference between these two. So when we do a hard cut of this particular zone, again you can see there are some compounds that are different between these two products. Okay, so this is the minute information that the R&D people will be looking at when they are doing some failure analysis or contamination analysis or a reverse engineering or deformulation analysis. For such type of application, hard cutting EGA GCMS will be very useful. Now let me go to the last part of my talk, okay, which is basically the micro reaction pyrolysis. As I said in the beginning, okay, not all samples can be done by a flash pyrolysis. In some cases, like the condensation polymer, you may have to use some kind of methylation of the reactive pyrolysis step. And even some type of condensation polymer, it is not sufficient to do the open reaction. You may have to use a closed reaction. Such reactions are possible with our system where we are using a glass capsule. Okay, in this glass capsule, what you are doing is you are taking your sample and the reagent, and you fuse the end, so that means it is closed. Then you attach to the sampler. Then you insert into the furnace where the temperature is set high for the reaction. So while heating, it's also closed, that is also developing some kind of pressure. So the sample actually, when you have this kind of sample, you know, with the temperature and also the pressure, it can reach this supercritical fluid condition. That means it can really help you to accelerate the reaction. Okay, that is important for some type of polymer analysis. At the same time, you can also assume this can be used for some of the organic synthesis where you want to do the reaction at micro scale, and because then you do not know how to see your reaction completion, you can just do it in this way, and you can analyze, you can see what kind of product is formed from your reaction. That could be possible with this. Okay, so here, since we are dealing with the polymer, we are showing an application on the polymer where I said generally the reactive pyrolysis with the tetramethyl ammonium hydroxide, okay, may be sufficient for polyesters or polycarbonate. But in the case of polyamides like nylon 6.6, the open system does not give sufficient efficiency. Okay, so one has to go for the alternate method like closed system, which is basically the micro reaction. So as I said, here the sample being heated in a closed condition, that helps like develop high pressure also. And it is easy to handle because you have a glass tube where you take the sample, then you fuse it with the flame, then you drop it inside. So you set your reaction time. Then you can push down this sampler that will crush the capsule. Then any compounds that are inside will be swept to the GC column for further analysis. So it's very simple, okay, in terms of the operation. So here is the output that you will get when you do the reaction, the micro reaction like reactive pyrolysis for a nylon 6.6. As I said, the flash pyrolysis cannot give a distinct peak for this monomer. The reactive pyrolysis with the open system, okay, gives some peak, but still they are not prominent. So what you see here with the closed system is more distinct peak, and also you don't have to go very high temperature. Okay, so you can see that difference also, particularly if you are doing flash pyrolysis, you are going to 600 degree. Here after the reaction, so generally your pyrolysis can happen at 300 degree, and here you are able to see this methylated compound of this monomer very distinct. So this is the advantage of this micro reaction sampler. As I said, it is not only useful for polymer sample, even as an organic synthesis chemist, even make use of this sampler for different type of reaction when you wanted to do it at micro scale. Okay. This is another example where people are trying to do the profiling of fatty acids. Fatty acids, again, you cannot do the direct analysis, even the GC. You have to do a FAME, the fatty acid methyl ester. So normally people use boron trifluoride, which is considered toxic. Okay. So the alternate method is always something they are interested in. So here what we have demonstrated, if you are using our microreaction sampler, you don't have to use the boron trifluoride, and you can just use the methanolic sodium hydroxide that will help you to do this methylation, and you can get very good kind of profiling that has got very good reproducibility, and it's in good agreement with the standard method of offline methylation with the boron trifluoride. As I said, people do not prefer to use boron trifluoride because of its toxicity, and when they see this is an alternate method that can give you same or better results with a better reproducibility, and this is the best thing that they want to have it in their laboratory. So this is another example where we wanted to show how the microreaction sampler or the microreactive pyrolysis can be used for different type of application. So with that, I just want to sum up my presentation. So as I started my topic saying that recent developments, I have shown a lot of accessories for the pyrolysis system that can actually expand the capability of analytical pyrolysis. So that means we can do evolved gas analysis, we can do flash pyrolysis, we can do double shot analysis, we can do hard cutting EGA GCMS, we can do reactive pyrolysis, we can do online microreaction, and UV radiation and oxidative pyrolysis. So my fellow speaker, Dr. Shogo, will be talking about these two. So with